Okay. We were talking about sort of adapting Newton's original theory to hypersonic flows. Newton assumed that any fluid impact on an inclined surface, or any surface for that matter, could be approximated as an exchange of momentum in which the normal momentum is completely lost in the impact and the tangential momentum is conserved. Or in other words, as a result of the impact, the fluid exerts a force in a direction that is normal to the plate and then spreads over it tangentially. Spreads over it tangentially. That's important. So, very few applications for this in real fluid flows, but in hypersonic flow, this finds an interesting application because many of these happens to coincide with what is observed in hypersonic flow due to the specific physics of it. So what we have been discussing is how this theory applies to, or the way that this theory can be formulated to a jet which impacts on a surface. So we have seen the conservation of momentum and the assumptions related to it in such a way that the Cp, that is pressure coefficient, defined as P minus P infinity divided by half rho infinity V infinity squared. P minus P infinity is the effective pressure on the that is impact that is experienced on the plate due to the impact, and that is normalized by the velocity head half rho V squared, so that we define Cp in the usual way as say P minus P infinity divided by half rho V squared. And the Cp can be because of just by the consideration of the tangential and normal components of momentum, the Cp can be equated as 2 sine squared theta, where theta is the angle of attack, that is the inclination of the surface with the mainstream, theta. Okay. So based on this formulation, so we have an expression where I mentioned that the importance of this is it gives some means to estimate the static pressure distribution, which can in turn be used for calculating drag, lift, air ratio, etc. on a surface. And we were also discussing these points, why Newton's theory is becoming important for hypersonic flows, whereas it has no applications practically in incompressible flows or even supersonic flows. But suddenly in hypersonic flow, some of the flow physics happens to coincide with the assumptions of Newton's. And that's what we were discussing about as streamline turning, which is applicable to supersonic flows also. Mach number independence, which we are going to see soon, and the near tangential flow. This is what I have been explained. That is, after the flow impinges because of the high Mach number and low theta for sharp bodies, the beta wave angle is also low. So that makes the flow to be parallel to the surface. I guess I've been explaining this. I'll try to the last point actually, the near tangential flow over a surface. That I'll try to explain with yeah. So please see that in this you have a included you have a corner angle of theta is 10 degree. That is, you have a compression corner where the theta is 10 degree, fairly low, not too low actually, but can be slightly on the lower side. Okay. And when you have a high Mach number like 32, we can see that, I mean, just by using tables or that portal, etc., you can check this. The for a weak shock formation, beta is about 18 degree. Not 18, I'm sorry. I don't remember the number correctly. When it is 10 and 32, I guess it comes to be something like 11 to 12, something like that. Okay, you can check that, the value of beta. So now look at the difference between theta and beta. It's very low, which means that after the impingement, now what is beta? The shock angle. Now the flow deflection after the formation of the shock is practically parallel to the surface. We are considering inviscid flow, so there is no viscosity, shear layer, etc. So it's parallel to the surface. Not only that, it's parallel, the region is very, very narrow. The curly bracket that I'm trying to show here. Now, why this region is very narrow? It's narrow because beta is very low. What is beta? Beta is this angle. Okay, that is the shock wave angle. So since beta is very low and since beta is very close to theta, you have a very small layer in which the entire flow is spreading over. Newton happens to have sort of conceptualized the flow in similar fashion. He assumed that in a small layer, the whole fluid spreads over the surface. And this is the reason why. So the momentum exchange theory becomes applicable when that layer is very small. Okay, whereas if you have a larger layer, right, as shown here, that is, if the angle is reasonably high, the beta is, if it is reasonably high, then you have a wider layer there. Then this theory doesn't become applicable. So that's the reason why Newton's theory becomes specifically applicable in hypersonic flow, and the applicability increases as Mach number increases. Okay, so this is why we are applying Newton's theory or trying to extend that to hypersonic flows. Any questions so far before we go to the actual formulation of the aerodynamic forces? Any questions on what we have discussed so far?
Excuse me, sir.
Yeah, please.
So in this case, we are assuming that the normal component completely becomes zero, right? Or that
Yes,
happens.
yes,
So
yeah,
the velocity becomes zero, v normal.
yeah. Yes. So that is in any case that is applicable, right? Okay. Sorry. You were asking something else. Okay. I'll come back to it, but complete your question. Yeah.
No, so that only.
That
Are
is okay.
this talking about the normal velocity completely going to zero or becoming small? Is my question.
No, actually, I mean the theoretical assumption is it is zero. That is this component. I am trying to show it. Okay. That is normal to the surface. You are not going to have a velocity, right? And as long as you have inviscid approximation, this is a reasonable assumption. As long as we restrict ourselves to low viscosity. So the theoretical assumption is the normal component is zero and the flow is fully tangential, or the velocity component is along the tangential direction.
Okay.
Okay. So what I'm trying to show here, I'm sorry, I'll just try to clean up the mess on the slide. Yeah. Now what I'm going to show is the two curly brackets which indicates the shear layer thickness. The shock layer thickness for hypersonic flow, and or rather low beta value and for high beta value. Okay, I'm just schematically showing. So I'm just trying to impress upon the fact that when beta is low, the entire flow seems to be almost spreading over the surface, so that the entire momentum is going to be experienced by the surface. Okay, and that's the reason why suddenly Newton's theory finds an application in hypersonic flow. It's a kind of you can say an unexpected turn of events, because there was nothing in the theory which would otherwise address hypersonic physics. But the basic assumption of Newton is more closely satisfied in hypersonic flow, and that is mainly because of this low thickness of the shear of the shock layer. Okay, now we'll go back to what happened or how we make use of it for aerodynamic forces. Again, it's quite straightforward because the theory itself is quite simplified one. So we are just considering the an inclined plate at an angle of attack. So what we are trying to do here is to derive expression for CL and CD for based on Newton's theory for a plate inclined at an angle of attack alpha with the mainstream direction. Okay, so the flow, the theory says that the flow comes, impacts on the surface. I'm trying to show impacts on the surface and becomes tangential to it. There is only the normal component of, or rather, if you were to resolve the normal component of force, we'll try to show the, I'll try to represent that on this side, the triangle that we have. Okay, you have the normal component of force, and just by the usual notation in aerodynamics, we consider the vertical component as L and the parallel to the flow component as D. So lift and drag. Okay, so the normal component, I'll just call it as Fn. Normal component of the force, we are resolving it as lift and drag. Now please remember that as per Newton's theory, the flow it's like an infinite plate that we are trying to consider here. So you can consider that okay, for infinite, you can consider the length to be L, and then the flow does not turn around as per the premises of the theory. The force is expected or experienced only on one side. Okay, so so even here in this this one, that notation N that is shown here is the force that is experienced on the face, the face that is towards the flow. Okay, not the leeward one. So when you have this kind of a resolution, now it's quite straightforward. The normal force component can be written Cn as N divided by Q infinity S. What is N? N is what I have written here as Fn. So you can rather take it as N. N, that is the normal component of force, divided by the Q infinity, half rho v squared, basically half rho infinity v infinity squared, and the projected area. Now we'll just consider and the area actually. We'll consider length of one unity and normal to the surface, because anyway that will cancel. So we'll just consider the length that is shown here is C, and normal to the plane we'll consider a unit length, so that S equals C into 1 C. So as per the theory, the Cn is equal to Cp. Why Cn is equal to Cp? Because the pressure Cp is the pressure distribution on the face where it is impinging, and there is no pressure on the other side, so you don't have to take a Cp1 minus Cp2 or etc., because it's only on one face. So Cn is equal to Cp, that is the coefficient of normal force is equal to Cp. So which in other words we can write as Cn is equal to 2 sine squared alpha. That's because we have already derived an expression for Cp, 2 sine squared theta here actually. That is basically the angle of inclination. So 2 sine squared alpha is equal to the normal coefficient of, or rather coefficient of normal force. Now just by the construction of this triangle which is shown here, we know that Cl can be written as L by rather Cl can be written as Cn cos alpha and Cd as Cn sin alpha, right? L and D indicating the coefficients of lift and drag in the respective that in the coefficients of lift and drag actually. So Cl is equal to Cn cos alpha, right? Just by that triangle, consideration of that triangle, Cl is Cn, that is the normal component multiplied by cos alpha. Similarly, Cd is Cn sin alpha. So now we know Cn is 2 sine squared alpha, so we just substitute it in both cases. So Cl becomes 2 sine squared alpha cos alpha, and Cd becomes 2 sine cubed alpha. I'm sorry. Cl is 2 sine squared alpha cos alpha, Cd is 2 sine cubed alpha, so that the ratio L by D is cot alpha. Sine gets cancelled and the whole thing becomes cos by sine. So L by D ratio can be written as cot alpha. Okay, so the ratio of lift to drag in this kind of a configuration for applying Newton's theory for hypersonic flow can be derived as L by D is equal to cot alpha. In fact, even this can be derived based on the for any inviscid flow for that matter. But then we are just showing that this applies for the derivation of aerodynamic ratio of aerodynamic forces based on the hypersonic theory, Newton's hypersonic theory, as applied to a flat plate inclined at an angle to the main stream. Okay, so all that we have done on the this in the discussion pertaining to this slide is resolving the forces in the resolving the normal force in the CL in the lift and drag directions, and then extending the formulation that we had to calculate L and D and the ratio of L by D. Okay, so no new physics introduced here. Okay, now let's see how this is being utilized, or rather before that, yeah, this we have. Yeah, okay, I'll just go to the Lee's modification also, and then we'll see how it is applied. The Newton's theory has been modified by his name is Lester Lee. I've seen this paper, fairly old paper actually, but then he proposed way to more accurately represent the pressure distribution. So he just modified. It's a small modification and it's quite intuitive also. I'll try to explain that. So Newton's theory as such, as we have seen here, the derivation is usually based on the attached shock. But Lee modified it in such a way that it can be applied even for detached shocks with fairly accurate prediction of the static pressure distribution on the body. So that is called Lee's modification. I'll come to that, but before that, I'll just go to, yeah. We'll discuss this graph. My intention now is just to show this body here, that blunt shaped body here. Blunt shaped body here, okay, in which you will expect a normal shock, a bow shock here. Now let's talk about this point. That is the point where you have that is the point just downstream of the shock, downstream of the normal shock region. Okay. Now let's talk about how we are say the Newton's formulation is for CP. Okay. Now my question to you is, if you were to consider the pressure distribution on this body, I hope this is clear. If you were to consider the static pressure distribution on this body, where would you expect the highest value of static pressure? I'll call it as P max. And I request somebody to answer that. Please remember to unmute and answer. Please keep in mind the picture. You have a blunt shaped body. You have flow, a supersonic or hypersonic flow. As a result of it, obviously we would expect the formation of a detached shock, a bow shock. And since we are talking about pressure distribution, keep in mind the Newton's theory is made use of to calculate pressure distribution on the body, CP. Now, at what point would you expect the highest static pressure?
At the tip.
Sorry, repeat that.
At the tip, sir.
At the leading edge, yeah. That's at the nose of it, right? This is what your point. This is what you indicate, right? The tip, the leading edge of the body. Is that right?
Yes, sir.
Why is that it is highest there?
Because the tip, we can see that the normal vector is almost towards the flow. So we can say that the plane of the normal vector is almost perpendicular to the horizon. I mean,
correct. That is correct, because what you are saying is about the directionality of the flow. In
yes,
addition to that, or more importantly, please note that that's a region where you have, or that's a prime region where you have the normal shock, right? So remember that across the normal shock, the static pressure increases. Now, if you look at the shock structure, you have a normal shock near the center line. As you go away, you have a you have an oblique shock. So static pressure rise is going to be highest across the normal shock, right? And the tip coincides to be a region where you have a normal shock, which is downstream of the normal shock, as well as it's aligned with the velocity vector, as you mentioned, right? So you have because of that, you have the highest static pressure in that region. Okay, so which means that the Cp max, when P is P max, we will have the highest value of Cp, because the normalization is with respect to mainstream half rho v squared, which is anyway mainstream value, which is constant. So when Cp is highest, we will have a highest value of Cp max. Okay, so what Lee proposed is that he kept that proposed that leading edge, the tip of the body, we can take P max as, or rather we can calculate Cp max based on P max. That is what is going to be the static pressure after the normal shock, and then subsequently you can use the Newton's sine squared theta formulation. Okay, now I'll go back. So this is basically the background of the Lee's modification. I'm just coming back to that. Please look at the pictures. They are all depicting detached shock formation. Okay, so basically all of them have a blunt body nose with a detached shock. Okay, now Cp max corresponds to the static pressure just behind the normal shock, because that is what is felt at the nose of the blunt nose of the body. Okay, so what Lee proposed is that he rewrote Cp as Cp max sine squared theta. That is because at theta equals 0, that is when you have the detachment point or the normal point, you will have the value of Cp exactly as per the normal shock relation. So Cp max is written as Cp is written as Cp max sine squared theta. So that of course then the whole thing comes as P naught 2 minus P infinity divided by half rho v squared, etc. But then with this modification, what he achieved was that at the tip of the body, or rather at the nose of it, the theory matched with the theoretical calculation based on normal shock relation. So that now the importance of this is that it made it closer in the case of particularly for detached shocks, because otherwise we will have a value which will be sort of under predicted in the case of detached shocks. So this is called the Lee's modification. Now let's see how it works actually. Please look at the graph. Now this graph is for this the body that is shown here. Because the pressure, the shape of the body is given as B equals 0.769 y squared minus 1, etc. Some particular experimental configuration. Okay, the body shape is as per that particular relation. Now the pressure distribution is plotted on that based on two methods. One is time march. We can consider it as a numerical method, like a CFD analysis. So which is an exact method actually. Okay. Now, so the solid the solid curve line that you see here is based on, which is what I am showing as the red line now, is based on a numerical method which is exact, that is without any approximations. Okay. Now the other one, that is the dotted one, is based on the original Newton's formulation, that is 2 sine squared theta calculation. Okay, and what you see as the dark dots, okay, in this representation, the dots are based on the modified Newtonian solution. Okay, so you can see that the dots, which are based calculations based on Newton's formula, modified, that is Lee's model, they actually coincide with the exact solution. Exact means the numerical solution. Okay, so for example, the tip you have, see p by p naught 2 is equal to 1. This, what is plotted here, is p by p naught 2. So p naught 2 is the sorry. The pressure distribution basically is shown on the this one. So you have the values coinciding for the accurate, the exact as well as the modified Newtonian method, whereas the Newton method is itself slightly away from the from the exact results. So two things to be noticed from this: even the Newton's original method is giving fairly close results, but the Lee's modification gives a better match, particularly when you have a detached shock. That's importance of Lee's Lee's modification. And now look at this graph also. I'm showing this data because to actually highlight how this theory, or why this theory is applicable, or why this theory is useful despite its say oversimplified approach. Now here you have actually three sets of data. Okay, one is the modified Newtonian, actually the modified Newtonian data plotted for m infinity equals 8 and m infinity equals 4. Okay, and so you can see that. This is the Newtonian calculation for when Mach number is 4, and this is Newtonian calculations for Mach number equals 8. Okay, and the dark dots are experimental. I guess they are experimental. I need to confirm that, but either experimental or exact calculation. Okay, theoretical. So the numerical. So I consider it as experimental. I need to be sure about it, but then I'll check that. So these are either numerical or experimental data, which are, let's consider it as accurate solution for the time being. So the black one, the dots represent the exact solution or accurate solution. Okay, we see that as Mach number. So the two things is, for 4 and 8 you have reasonably good close, and it's even closer for 8, which means that as you increase the Mach number, they tend to merge to the accurate values or the exact results. That's the utility of Newton's method. As Mach number increases, you get a better match with the experimental or exact calculation of the static pressure distribution for bodies of really not too complex shapes, actually, either a sharp nose or even with Lee's modification, even for blunt shaped bodies. Okay, so but then keep in mind, we are focusing our analysis to inviscid flows. So you may have all the limitations of inviscid flows, and then Newtonian theory itself is a simplified approach. So you will have further simplifications because of all that. But despite all that, it gives a useful estimate of the pressure distribution on the body. So once you have the pressure distribution, as you have seen, we can calculate CL/CD and the aerodynamic, the related aerodynamic factors quite easily. Okay, so that's where the applicability of Newton's theory as applied to hypersonic flow is. Now, what we are going to do next is 2:35. Yeah, I'll stop now. What we are going to do next is see the approach that we have in this course is look at how pressure distribution is calculated or how the flow physics is addressed based on different approaches in the increasing level of complexity and in the increasing level of accuracy. So we are starting off with Newton's method now. Now next we'll go to the next level, which is the shock expansion method. People call it as shock expansion theory also. So which is basically a combination of shock theory and the expansion theory. So how they can be used to calculate the pressure distributions is what we are going to discuss next. Okay. I guess I'll stop here, but then we will get on to the presentations also. Can I request the, okay, so if you have any doubts, I'll address them right away. Any questions? Okay, then we'll move on to the remaining time we'll try to use for the discussion of the assignment problems. I guess yes, today I didn't check anything, but yesterday I checked nobody had submitted. But so what's the status today? I hope everybody has submitted. I will not check that. I had requested you to submit, upload it all in the assignments folder. That's where I checked actually, unless you have kept it somewhere else. So can I ask group 1 to come forward and present your results? Sorry, group 2 to present your results. I will stop sharing. Yeah, great. I can see the this one. Before that, 1 second, please. Before you start it, just confirm the presence of, yeah. Group 2, roll number 23, Lakshmi Shivakumar, 23.
Yes, sir.
And K Naresh, 25. Naresh.
Yes, sir.
Nitin, 26.
Yes, sir.
And then Niveta,
Yes, sir, present, sir.
Praveen.
Yes, sir. Pawan, sir. Yes, sir.
Fine. So 1 second, I'll just mark the date here. So 30 hours, 0308. Yeah, great. Please, you can start. You can just explain your result.
Yes, sir. Good afternoon, sir.
Good afternoon.
Sir, let's go to the next slide. So, based on the given values.
Sorry, are you in slideshow mode? Are you in?
No,
Have you
sir.
put that on? You can, right? That's better. Clarity will be better.
Yes, sir.
Good. That's better. Yeah, please carry on.
Yes, sir. Now we are going to present on validity and applicability of hypersonic limit approximation. So here is beta theta radiation, which we modified from the hypersonic limit, applied the hypersonic condition where m tends to infinity. So from the given theta values, we got the beta values for the hypersonic condition. Next. So from the oblique shock tables, we got the data for a particular theta deviation of deviation angle. For a particular Mach number, we got the beta values. We got for weak and strong shock conditions. For weak shock, we can see the decrease in beta value for increase in Mach number, which we see in the graph mode. Next.
Please, no, stop there. You please highlight what you said now. That's an important observation, but just for everybody to be sure
Yes,
about
sir.
what you're. That is the
For a
difference in
particular
beta,
for a
the difference
particular
in trend of beta. Yeah, please
yes,
highlight that. Yeah.
for a theta, for a given theta, the beta value decreases with increase in Mach number.
Yeah. And for a strong shock.
For a strong the same, it is increasing with increasing Mach number. Beta value is increasing with increasing Mach number.
Yeah, fine. Okay. There
Which you see in graphical form. For a theta is equal to 5 degrees, in the hypersonic condition we got exact value as 6, beta value as 6, and we can see the blue line which is going to which will go to 6 linearly with at very high Mach numbers. This is the same for strong shock. The values increase and go to the constant value 88 and 86. Here the observations from the theta beta m relations, we can see beta value decreases for the increase in Mach number, and we can find the beta value directly from the hypersonic limit condition for the Mach number, and both the values of beta match when the Mach number is very high. So we can apply the hypersonic limit condition can be applied, and the beta value found can be used when the Mach number is very high.
One second. Can you just say that third point? Can you go to the graph and then show it on this? That is, we are saying that with this you tell me you explain that third point once again. Show the graph and explain. Whatever. Yeah, and explain it. Yeah.
Yes, sir. If you consider theta is equal to 5, which is the blue line, which is decreasing with Mach number, increasing Mach number. After a certain point, there won't be any means high deflection in beta, which would be constantly reduced to 6 degrees at very high Mach number.
So what do you have along the x-axis in this?
Along the x-axis, it is Mach number, sir.
Mach number, yeah. So at with increase in Mach number, what you have on the y-axis is beta, right?
Yes, sir. It
So
is going to the value we attain with the hypersonic condition, which is 6. We can attain the same value in this condition at very high Mach number.
So basically, that it approximates, or rather, it goes close to the higher value, the value
Yes,
of.
when we go to 1000 Mach number 1000 like that, the 10 power minus 2.
That approximate, yeah, it
Yes,
comes
sir.
to be
Constant.
And the two graphs, one is for theta equals 5, and other is for theta is 15.
Theta equal to 15 degrees, sir. And the above one goes to 18.
Okay.
That's it.
Okay. Now, okay. You please don't just share that once again. The slide. Go to the first, this one, the statement of your program. No, the first slide, the statement of the problem or the question. Second, I'm sorry, the next, the validity and applicability of hypersonic limit approximation for V by the beta theta relation. No, +1 by 2. So where? Okay. Can someone else in the team answer? What would be the effect of the gas on this? What if you were doing? Well, first of all, what value did you assume for the gaseous property on this in this whole calculations?
So
Anybody
we
other?
took gamma equal to 1.4. So this is Niveta.
Omega is 1. Okay. Now I assume that you did the whole calculation for a different gas. What would have been that impact on it?
It depends on what the gamma is for that particular gas. So
Yeah.
unless the gas is calorically perfect, there shouldn't be it won't be applicable because as the temperature increases, which is pretty inevitable in hypersonic flows, for thermally perfect gases, the gamma value will change with change in temperature. So I think this formula is valid for calorically perfect gases where the gamma does not change with an increase in temperature.
I agree with that. No, that's correct. But my question is qualitatively. So maybe someone else, Nitin, can you please answer that? Qualitatively, would you see any differences in the observations if you did the calculations for say gamma equals 1.2? Nitin. Roll number 20 to 26. Hello. I guess he's present, right? I need some answer. If you don't know, also, I mean, I said, even if you don't know, it's an answer, but then please respond when he asks something. Again, we'll go to group 3. Can you please? I guess we have. Do we have time? Okay. Okay. We'll stop here. We'll continue in the next class. So other groups and all of you actually, please upload if you have not done it already. Please do upload the presentations in the assignment folder. Okay, of the team. Okay. So please upload the presentations today itself, and I will request the remaining teams to do the presentations in the next class and the class after that. Okay, I'll stop here today. Thank you. Thanks to all of you. Bye.
Thank you, sir.